two projects. In this video, we are going to explain about the project title Attention-Based Cross-Model CNN using non-disassembled files for malware classification. Introduction. The project aims to categorize various malware instances into families or types. The increasing volume of malware variants poses a challenge for traditional methods that rely on manual analysis. Disassembling malware codes is a common technique but presents difficulties due to the evolving nature of malware and anti-disassembly measures. Deep learning methods have proven effective in automating feature extraction from both dynamic behavior and static features. This automated learning process has shown promise in differentiating between various malware families. Extracting static features from disassembled files is valuable but has limitations. Disassembly challenges arise from complex code structures and anti-disassembly techniques embedded in malware, affecting the accuracy of feature extraction and classification. Multi-modal learning, which combines information from different sources, has demonstrated effectiveness in malware classification. However, even when using static features from disassembled codes as one modality, the project acknowledges that limitations due to disassembly persist. The proposed model in this project takes a unique approach by focusing on non-disassembled files. It combines two modalities, malware images and structural entropy. By utilizing a cross-model attention mechanism, the model aims to fuse these diverse modalities effectively. This attention mechanism helps the model learn associations between the image-based features and structural entropy, enhancing feature representation for accurate malware family classification without the need for disassembly. Objective. The primary goal is to create a malware classification model that doesn't rely on disassembled codes. This departure from traditional methods aims to achieve accurate classification of malware families without the need for disassembly, addressing the limitations and challenges associated with disassembling malware. The model integrates two different types of data modalities, malware images and structural entropies. By utilizing bytes and chunks in the two modalities, the model compensates for the limitation of each modality. This approach accounts for different levels of detail within the data, potentially improving the model's ability to capture diverse aspects of the malware. The model utilizes a cross-model attention mechanism to effectively combine the features extracted from the two modalities. This mechanism allows the model to learn associations between features from malware images and structural entropies, enhancing their descriptive and predictive capabilities. The project aims to validate the proposed model using well-known datasets such as Microsoft Malware Classification, MALI-MG, and BODMAS datasets. The objective is to showcase the model's superior accuracy in identifying and classifying malware families compared to previous methods, establishing its effectiveness in practical applications. Software and hardware requirements. Software requirements of the project are: software is Anaconda, primary language is Python, front-end framework is Flask, back-end framework is Jupyter Notebook, database is SQLite3, front-end technologies used in the project are HTML, CSS, JavaScript, and Bootstrap 4. Hardware requirements of the project are operating system of Windows, processor of i5 and above, RAM of 8 GB and above, hard disk of 25 GB and above. Working modules or flow of work. To implement this project, we have designed the following modules. The first module is importing the packages. This module involves importing necessary libraries and packages. We imported Pandas for data manipulation, NLTK for natural language processing tasks, scikit-learn for machine learning algorithms, NumPy for numerical operations, and Matplotlib and Seaborn for data visualization, Keras and TensorFlow for deep learning. Exploring the dataset. Microsoft Malware Classification. This dataset contains samples of malware instances collected by Microsoft, categorized into various families or types. Mali MG, this dataset consists of images extracted from malware instances representing visual features or patterns within the binary files. BODMAS, this dataset contains structural entropy or other characteristics derived from the non-disassembled binary files. Structural entropy measures randomness or complexity within the file structure. Image processing using image data generator. This is a tool provided by libraries like Keras for on-the-fly data augmentation. The operations listed below are transformations applied to the images to enhance the dataset's diversity and robustness. Rescaling the image, normalizing pixel values to a specific range, usually between 0 and 1. Shear transformation, distorting the shape of the image by shifting one part of the image in a certain direction. Zooming the image, adjusting the zoom level of the image. Horizontal flip, flipping images horizontally, creating mirrored versions. Reshaping the image, modifying the shape or dimensions of the images to fit the model's input requirements. Feature extraction, reading the image. Loading and reading images from the dataset, a critical step in preparing the data for subsequent processing. Resizing the image. Resizing ensures that all images in the dataset have the same dimensions, which is necessary for feeding images into neural networks. It helps standardize the input size for the model, reducing computational complexity and ensuring uniformity in processing. Convert the color. This step involves modifying the color scheme or channels of the images if needed. For example, converting color images to grayscale or changing color formats RGB to BGR or vice versa to match the model's expected input format. Consistency in color representation is crucial for model training. Appending the image and labels. Here, the images and the corresponding labels, which indicate the malware family or category, are paired or combined. This association ensures that each image is correctly labeled with its respective class or category, allowing the model to learn associations between the images and the classifications during training. Conversion to NumPy value. Machine learning frameworks like TensorFlow and PyTorch work with numerical data represented as arrays. Converting images into NumPy arrays allows for easier manipulation, processing, and compatibility with these frameworks. Each image is transformed into a numerical matrix format, often with pixel values normalized between 0 and 1. Label encoding. Machine learning models generally require categorical labels like malware families to be represented numerically for training. Label encoding is a technique used to convert categorical labels into numerical format. For instance, if there are different malware families, label encoding assigns a unique numerical value to each category, enabling the model to interpret and learn from these labels during training. Building the model. This step involves constructing the architecture of the attention-based cross-modal CNN. It comprises multiple layers, including convolutional layers for feature extraction from images, fusion layers for combining multiple modalities, and attention mechanism to focus on relevant features. Training the model. With the architecture defined, this phase involves feeding the pre-processed data into the model, specifying parameters such as batch size, number of epochs, and learning rate, and optimizing the model using a loss function and an optimizer. The goal is to train the model to accurately classify malware families based on the provided non-disassembled data. Flash framework with SQLite for sign-up and sign-in. Utilizing the Flash framework, this module implements a web application. It includes functionalities for user authentication, sign-up, and sign-in. SQLite, a lightweight relational database, is used for storing user information securely. User upload an image for analysis. Users interact with the web interface to upload malware images they want to analyze. This input serves as the basis for the model's prediction. The given input is pre-processed. Before inputting the user uploaded image into the trained model, pre-processing steps are applied, such as resizing the image to the required dimensions, converting colors if needed, and preparing it for analysis. The trained model is used for predicting the result. The pre-processed input image is fed into the trained model. The model predicts the malware family or category based on its learned features and associations between images and structural entropies. Final outcome is displayed through frontend. Finally, the predicted result, indicating the identified malware family, is displayed to the user through the frontend interface of the web application. This frontend component provides a user-friendly way to interpret and understand the model's analysis. Algorithms used to implement this project, we have utilized the following algorithms. The first algorithm is XGBoost. Extreme gradient boosting is a popular and powerful gradient boosting algorithm used for both regression and classification tasks. It's an ensemble learning method that combines multiple weak learners to create a strong predictive model. In the context of malware classification, XGBoost is used as a baseline or an alternative to deep learning models. It's known for its efficiency in handling structured data and feature importance analysis. It is employed to handle extracted features or metadata derived from malware files. VGG16. VGG16 is a convolutional neural network CNN architecture known for its simplicity and effectiveness. It consists of 16 layers, 13 convolutional and 3 fully connected, and is particularly famous for its use in image classification tasks. VGG16 is used for feature extraction from malware images. The pre-trained VGG16 model, fine-tuned or used as a feature extractor, can capture high-level features from the images. These features then be fused with other modalities like structural entropies within the cross-model CNN architecture. CNN, Convolutional Neural Network. CNNs are a class of deep neural networks designed for processing structured grid-like data such as images. They consist of convolutional layers, pooling layers, and fully connected layers capable of learning hierarchical representations from the input data. CNNs are fundamental in image analysis tasks. In this project, CNNs are employed as standalone models or as components within the attention-based cross-model architecture for processing and extracting features from images without disassembling the binary files. Modified attention CNN. A modified attention CNN incorporates attention mechanism into a CNN architecture. Attention mechanism allows the network to focus on specific parts or features of the input data, improving its ability to capture relevant information. The modified attention CNN specifically tailored for this project uses cross-model attention mechanism to fuse features extracted from different modalities like images and structural entropies. This fusion enhances the model's ability to understand relationships between these modalities and improves classification accuracy. As an extension, we applied an ensemble method combining the predictions of multiple individual models to produce a more robust and accurate final prediction. Comparison graphs. Comparison graph offer a visual breakdown of how a model performs across essential evaluation metrics. Models are compared with the parameters accuracy, precision, recall, and FN score. These are the comparison graph of bot dataset. This is the accuracy comparison graph. On the x-axis, we have accuracy score, and on the y-axis, we have algorithm name. Accuracy is a measure of the overall correctness of a classification model. It calculates the ratio of correctly predicted instances, both true positive and true negative, to the total number of instances. This is the precision comparison graph. On the x-axis, we have precision score, and on the y-axis, we have algorithm name. Precision is a metric that assesses the accuracy of positive predictions made by the model. It calculates the ratio of true positives, correctly predicted positive instances, to the total number of positive predictions, true positives plus false positives. This is the recall comparison graph. On the x-axis, we have recall score, and on the y-axis, we have algorithm name. Recall, also known as sensitivity or true positive rate, measures the model's ability to correctly identify all relevant instances in the dataset. It calculates the ratio of true positives to the total number of actual positive instances, true positives plus false negatives. This is the FN comparison graph. On the x-axis, we have FN score, and on the y-axis, we have algorithm name. FN score is the harmonic mean of precision and recall. It is a balanced measure that considers both false positives and false negatives. It is calculated as 2 times the product of precision and recall divided by the sum of precision and recall. It provides a single metric that balances precision and recall, making it useful when we want to consider both false positives and false negatives in the evaluation. The algorithm, which is performing best in all the performance metric, will be used for prediction. Comparison graphs of big 2015 dataset. This is the accuracy comparison graph. This is the precision comparison graph. This is the recall comparison graph. And this is the FN comparison graph. The algorithm, which is performing best in all the performance metric, will be used for prediction. In this project, we have also utilized Mali-MG dataset. These are the comparison graphs of Mali-MG dataset. Execution. To execute this project, first we need to open the code folder which contains the project source code files. This is the code folder. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is the templates folder. This folder contains all the HTML pages used in the project. It includes files like index.html, about.html, and more, which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. These are notebook.ipynb file. These are Jupyter Notebook files which contain combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. These are model files which contain algorithm information which will be loaded into the project code during runtime. This is signup.db file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the file explorer. So here, I'm copying the path. Now open the Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. So here I'm typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address, localhost, which is this, and port, which is this. Now copy this local link provided by the Flask framework. I'm copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. If we are a new user, we need to register first. So click on register button here. So here we need to enter all these details to register, but I have already registered. So click on sign in link here. So here we need to enter the username and the password which we have registered and then click on sign in. We have logged in successfully. So here we can see a classification link. We can execute the project using the 3 data sets. First, we will execute the project using big 2015 dataset. So click on big 2015. So here we need to upload the image and the image size should be less than 500 KB. After uploading the image, we will predict the malware attack type. Now click on choose file. Select the image, click on open. Now click on upload button. This is the uploaded image and here we can see the result. Malware attack type is Kelios version 1. Let us upload some more images and check the malware attack type. Click on classification link. Click on big 2015 dataset. Now click on choose file. This is the uploaded image and it is predicted as Malware attack type is Kelios version 3. Let us upload some more images. This is the uploaded image and it is predicted as malware attack type is Ghatak. Click on choose file. Click on upload button. This is the uploaded image and it is predicted as malware attack type is lollipop. Now click on classification link, big 2015 dataset. Now click on choose file. Select the image. This is the uploaded image and it is predicted as malware attack type is obfuscator ACY. Let us upload some more images. This is the uploaded image and it is predicted as malware attack type is SIMDA. In this way, by uploading the image, we can predict the malware attack type using big 2015 dataset. Now we will execute the project using another dataset which is BODMAS. So click on BODMAS. So here we need to upload the image. Click on choose file. Select the image. Click on upload button. This is the uploaded image and it is predicted as malware attack type is dialplatform.b. Let us upload some more images. Click on choose file. This is the uploaded image and it is predicted as malware attack type is agent. Select the image, click on upload button. This is the uploaded image and it is predicted as malware attack type is auto run. Click on choose file. Click on upload button. This is the uploaded image and it is predicted as malware attack type is browsefox. Let us upload some more images. Click on choose file. Select the image. Click on upload button. This is the uploaded image and it is predicted as malware attack type is androm. In this way, by uploading the images, we can predict the malware attack type using the BODMAS dataset. Now we will execute the project using the MaliMG dataset. So click on MaliMG. So here we need to upload the image. Click on choose file. Select the image. This is the uploaded image and it is predicted as malware attack type is uno.a. Click on classification link. Click on MaliMG dataset. Click on choose file. Click on upload button. This is the uploaded image and it is predicted as malware attack type is agent.fii. Let us upload some more images. This is the uploaded image and it is predicted as malware attack type is Sweezer.gen. In this way, by uploading the images, we can predict the malware attack type using the MaliMG dataset. Now click on logout button. The conclusion of the project is the proposed CNN-based model achieves precise classification of malware families without the need for disassembled codes. This approach simplifies the analysis process and effectively categorizes malware variants without the burdensome task of code disassembly. The model seamlessly integrates two distinct data modalities, malware images, and structural entropies, leveraging their complementary nature in capturing different levels of granularity within the malware data. This union provides diverse perspectives, combining fine grained details with broader structural insights. Through the use of cross model attention mechanism, the model aligns and reinforces the representations derived from malware images and structural entropies. This process ensures consistent lens between modalities and enhances the model's understanding of chunks present in both data types, leading to more effective information representation. The model's superior performance compared to baseline models, especially when dealing with malware variants having a limited number of samples, validates its effectiveness. This highlights its robustness and ability to achieve accurate classification even with sparse training data, showcasing its practical applicability in real world scenarios.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.